Vectors Part 4, Magnitude of Vectors. If R is a column vector with x units on the x-axis direction and y units on the y-axis direction, then we can see that there is a right angle triangle here. How do we find the magnitude of vector R? Now, you can use the Pythagoras theorem. So, given that A is 5 and 3, find the magnitude of A. So that will be square root of 5 squared plus 3 squared. And you get 5.83 units. Now how do we find magnitude of B? It will be square root of 2 squared plus negative 1 whole thing squared. Now we'll get the answer to be 2.24 units. And for part C, we should be able to get the answer 5 units. Have you gotten the answer? Now for a scalar multiple of the vector R, it does not matter whether is it a positive scalar vector or whether it's a negative scalar vector, the magnitude remains a positive number. So for example, the magnitude of 2R vector is the same as the magnitude of negative 2R the vector, and then hence it will be considered as twice the magnitude of R. So let's say if I have a vector with R, okay, then if I want to draw 2R, it will just be 2 times the length of R and in the same direction. So there's 1 unit here, and this one will be 2 times. If I were to have vector negative 2R, it means it's going in the opposite direction, negative 2R, but the length of the vector is still 2 times. So the negative sign in this case only tells us the direction. Now let's try to find out the following answers for question number 2. So length of 2C will give you magnitude of 6, 8 and square root, and we'll get the answer of 10 units. If I have to find 2 times of magnitude of C, it will be 2 times the square root of 3 squared plus 4 squared, and that gives me 10 units as well. If I were to have magnitude of negative 2 times of vector C, then I will need to change the sign. That will become negative 6, negative 8, and square root of negative 6 squared plus negative 8 squared. Now when we square the negative number, it remains as positive, so still be 10 units. Therefore, what we said for this property over here is true. Okay. Now, however, we should take a look at other types of vectors that can be easily mixed up. Okay, so now let's take a look at the magnitude of A plus the magnitude of B. That means we're finding magnitude of A plus the magnitude of B, and that gives us square root 5 squared plus 3 squared plus square root of 2 squared plus negative 1 squared, and we'll get the answer to be 8.07 units. However, if you define vector A plus B magnitude of vector A plus vector B, that will be, we need to do the addition first. I'll get 7 and 2, and I'll take square root of 7 squared plus 2 squared, and that gives me 7.28 units. Notice that what we have down here, vector A plus vector B and vector magnitude of A plus B, they have the different length. Now, why is this so? Let's consider the following vectors. Now, if it's vector A is the column vector 5, 3. B is the column vector 2, -1. And what should we find out for A plus B? Now, in a vector form diagram, A is vector A, it means 5 units to the right and 3 units upwards. So this will probably be vector A. And then we have vector B, 2 units to the right, 1 units down. And this will be vector B. But what is vector A plus vector B? Vector A starts from here, continue, and ends here. So this will be vector A plus B. Look at the different portions. If I were to have magnitude of A, which is the length of A, plus the length of B, this length will definitely not be the same as the magnitude of vector A plus B. So this length over here will be different from the rest of them. So that's why what we know, magnitude of A plus magnitude of B is not equals to magnitude of A plus B due to the triangle law of addition. Now let's continue with our remaining questions. We know that we want to find 2A, magnitude of 2A minus B. So we need to process the vectors first. We get 10, 6 minus 2, -1. And simplifying, it becomes magnitude of the vector 8, 7. And then we'll get the answer to be 8 squared plus 7 squared to be 10.6 to 3 sig figs. Have you gotten the answer? Now, how do we answer this type of question? Given that D to E is 2, -3, and D to F is 4, 5, find the magnitude of EF. That means we'll need to first find the vector E to F. How do we find the vector E to F? Starting at E, where can I connect to? E can connect us to the point D. And then from D, we are going to move to F. Now, DE and ED are opposite vectors. That means they'll be negative of each other. And we'll simplify to find the answer for EF to be this. Now, next, find the magnitude of this vector. We'll get EF to be square root of 2 squared plus 8 squared, where the answer will be 8.25 units. Question number 4, PQ is this vector and RS is 6T. Now T is the unknown. The question says that RS is parallel to PQ. Now when we talk about parallel to PQ, we'll have two concepts. The first concept is such that RS is equals to a scalar multiple times of PQ. Or concept number 2, we can say that the gradient of RS is equals to the gradient of PQ. So now what we are going to do, I'm going to use method 2, the gradient, to help us find the value of T easily. Now, in order to find the gradient of a vector, what do we do? Well, we take the y, which is the rise, over the x value, which is the run. So gradient of PQ is -4/3. This is equals to the gradient of RS. So RS will be the gradient T/6. Cross multiplying, we can get our answer. And in this case, T will be equals to -8. Now let's find the magnitude of RS. So magnitude of RS is magnitude of the vector 6, -8. And that gives us 6 squared plus -8 whole thing squared. Bear in mind when you press the calculator, the negative sign should be inside the bracket. And we'll get the answer 10 units. Question number 5, the quadrilateral WXYZ is such that so and so forth. Now we must make sure the points flow in the particular direction. Okay, so they must go from W to X, X to Y, and then Y to Z. Now they gave us the following vectors. We notice that this is 2V and this is negative 2V, meaning they are the same length but in opposite direction. Okay, and they tell me, oh, the length of U is equal to the length of V. So when we measure, we need to draw appropriately with measurements. So now let's start to sketch quadrilateral WXYZ. From W, I have to draw a vector U. Let's say this is 1 cm, or maybe more than 1 cm. Okay, I shall use 1 cm then to be vector U. Okay, so from W, we go to the point X over here. Now we're going to continue from X to go to Y. I do not know which particular direction, but I can roughly just go to in any direction that's different from U. So maybe I'll travel here, and I need to make sure that this length here is twice the length of vector U. And this will be vector 2V, and I'll end up at point Y. Now the next part over here, they did not tell us how to go from Y to W, but they told us to go from Z to W. Now we know that this vector over here, they are actually equal but opposite in direction. So that means in order to join to W, I will also have a length of 2 units going in the same length, say parallel to XY, and this will be point Z, but it's going in the opposite direction, negative 2V. If to complete this, then this diagram will look like a parallelogram. So what's the name of this diagram? Parallelogram. Express YZ as simply as possible in terms of U and Y. Now Y to Z is going in this direction, and comparing to this, we will have the opposite direction, negative U for the answer. So therefore YZ is simply negative U. We have come to an end to this part of the chapter. Let us summarize some of our learning points. Number 1, to find the magnitude of a vector, we need to use the Pythagoras theorem, where the magnitude of vector R will be square root x squared plus y squared. Magnitude and property number 2, magnitude of A plus B is not the same as magnitude of A plus magnitude of B due to the triangle law of addition. And thirdly, the magnitude of positive scalar vector of and a negative scalar vector are all the same as 2 units of the same vector. The sign does not have an impact on the length of the magnitude of the vector. Up next, we'll move on to vectors, part 5, position vectors. See ya!